ordering. So the happened before relation that was defined by Lamport, and then how the happened before relation can be implemented, and then we can build clocks like logical clock, Lamport's logical clock, that we can use to recognize, basically to implement a relation where if A happened before B, then we are guaranteed that the logical clock value of A will be less than logical clock value of B. Okay? But the reverse was not necessarily true. Okay? And so then we went on to look at vector clocks. And the vector clock basically implements this relation, which is if A happened before B, okay? No, or A happened before B, if and only if the vector clock value of A is less than vector clock value of B. Okay? So you can use vector clocks to recognize what are called concurrent events. Okay? So that's basically what we had in our, and then we basically started looking at the physical clocks, because we have applications where we want to actually relate the events that are happening in a distributed system with the real time. Okay? And in order to do so, we have to basically synchronize the clocks of our computing system with the real time clock. So we looked at some basic algorithms. Okay? And what we are going to look today is a very popular protocol. It's called Network Time Protocol, or NTP in short. Okay? And this is a protocol. It has been in use under various versions, probably since mid-80s or so. Okay. So I think the first version of this protocol was started running sometime in 84 or 85. Okay. And it has been in use since then. Of course, it has gone through many revisions. The current version that we have, which is the Internet Standard, is version 4. Okay. And the basic idea of NTP is it's a distributed time synchronization protocol, and it's basically a clock protocol that runs over packet switch network, so basically our internet kind of network. Okay. And the idea is to keep all computing systems, pretty much all computing systems, synchronized with the with UTC, okay, the universal time. Okay. It's a very popular protocol. Pretty much every computing device that we can think of, our cell phones, our embedded devices that are there in cars and things like that, and of course our laptops and desktops, all of them, they run NTP. Or actually there is a simpler version of NTP. It's called SNTP, Simple Network Time Protocol. So the smaller devices like embedded devices, they will probably be running SNTP. Okay. But it's a very extremely popular protocol. The details you can find actually if you go to this website, ntp.org, and it basically gives you the latest developments that are there in this protocol and all the details, And the basis of this protocol came from this PhD dissertation, although there were other work also that have influenced the design of NTP, but this is basically one of the dissertation that actually led to the development of NTP. So NTP, and basically the main goals of NTP are to enable clients across the internet to accurately synchronize their clocks to UTC despite message delays. Okay. So we looked at in the previously the basic protocol for synchronization is pretty straightforward, right? You send a message to the time server, receive a message, and then synchronize your clock. The problem comes because the latency, the message delays themselves are not deterministic. You don't know how long it takes for the message, and it varies from time to time. Okay, so even though the time server says that the current time is so and so, okay, and you really don't know exactly how much the message delay was, and so it gets difficult to synchronize your clock, right? So the idea behind NTP is to use statistical techniques to filter out the erroneous data. Okay? And it actually relies on history. So it basically looks at the past readings, and based on that, it basically gets the good quality of data to synchronize its clock. Okay? It provides a reliable service. So basically, it can survive lengthy losses of connectivity. It has redundant paths, redundant servers. Okay, so naturally, I mean, you're using this to synchronize pretty much every computing device in the internet. So you must have redundancy in the servers as well as in the paths. And so it enables clients to synchronize frequently. So basically, we saw that in our in the lecture that I recorded, we saw that the clocks have their own drift, right? So once you synchronize the clocks, over time they will again drift. Okay, and so NTP is designed to basically have your clock synchronized at pretty regular intervals, so that they don't drift apart from one another too far apart. Okay. They provide protection against interference. So this is another thing, because now we are talking about synchronizing devices, all the devices over the internet. So security is naturally a very big concern here. Okay. And so the protocol actually provides a mechanism where you can authenticate the source of data with which you are synchronizing your clock, and so on. Okay. The other thing is it provides a statistical filtering of timing data. So it basically discriminates different data that it collects, okay, based on the quality of data from different servers. It basically is based on some inter-server connections. There is actually a logical hierarchy that is built by NTP, okay, and it's designed to be scalable for both the clients and the servers. Okay. And then, as I said, authentication of the trusted servers. Okay. So the synchronization accuracy that it provides, it could be within tens of milliseconds over the internet path. So if you are on the internet, you will be able to synchronize your clock within about tens of milliseconds. NTP also runs over local area networking environment. And there you can actually synchronize your clocks to within 1 millisecond of UTC. So the hierarchy for NTP is basically, it maintains this hierarchy of servers, and each of these servers here, they are defined or classified by what they call a stratum. Okay, so the top one actually I have not shown here, which is what is called a stratum 0. Okay. And stratum 0 is basically pretty much any timekeeping device, the high precision devices. So basically these are the atomic clocks and whatever the cesium clocks and things like that. These are the ones that have the actual time. Okay. So these are the stratum 1 are basically the machines that are directly connected to these time sources. Okay. So these are basically the sources that have either connected to atomic clocks, directly connected, GPS, they have GPS clocks, radio clocks, The idea is that with this arrangement, the stratum 1 servers, they have their clock synchronized within few microseconds of the actual time servers, to time. Okay. And then after that, the next thing is the second stratum servers. Basically, these are the servers that are connected to the stratum 1 servers, okay, and they of course interact with the stratum 1 servers to receive time. The other thing that I have not shown here is that these servers actually do peer-to-peer connection within one another also, okay, and it's the specification says this is a sanity check, that is, like if you're synchronizing with the stratum 1 servers, your clock is supposed to be this, so you check with your, peers in the same stratum to make sure that indeed that is the case. Okay. Okay. And then you can have, level 3 and all. In the specification, you can go all the way to stratum 15. Stratum 16 is considered completely unsynchronized system. And the larger the stratum number server is, more liable to be less accurate. So that's basically this. The synchronization mode for NTP is you have the multicast mode, which is basically used in a LAN environment. And it turns out that in a LAN environment, depending on your multicast protocol, it could be less accurate if you're using the multicast mode. In the LAN environment, you can also use the unicast mode, the RPC mode, but you can use multicast mode also. Multicast mode happens to be less accurate, and that has to do with the implementation of the multicast protocol itself, actually. Okay. And also it has the procedure call mode, and this is something similar to the Christian's algorithm that we looked at with the probabilistic clock synchronization protocol, we looked at earlier. Okay. It also has symmetric mode, which is intended for servers to synchronize with one another. So the pairs of servers can exchange messages between one another, and this basically helps them to improve synchronization over time. Okay. Now, all these basically the basic communication protocol that is used for these by all these modes is UDP. Okay. So as you know, UDP is unreliable, meaning that your messages may be lost when you are using UDP. Okay. And UDP does not guarantee any FIFO guarantees or anything like that. So when you send two messages in UDP, those messages may be received in a different order than the order in which they were sent. But basically, this is built on top of UDP, and the main reason, again, the reason it is built on top of UDP, there are two reasons. One is that UDP is, if you just look at the latency point of view, okay, UDP turns out to have less latency than a TCP connection. Okay, so that's one reason. And the second reason UDP is used instead of TCP is because UDP does not require any connection. Okay, and that actually helps in scaling the whole protocol over essentially millions of servers and clients. Okay, so those are the two reasons why UDP is used, instead of something like a more reliable protocol like TCP. Okay. Yes.
Is there a multicast TCP, or is that just UDP on a LAN?
This is all UDP. Okay, the multicast is all UDP. You're talking about for NTP, right?
Well, I was actually asking in general.
Oh, in general.
I don't know.
So TCP is point-to-point. Now, by definition, the TCP is always a point-to-point protocol. It's not a multicast protocol. Now, there is IP multicast protocol. So you can basically build an application layer protocol that uses IP multicast to do the multicast.
Okay. Yeah.
So, in the procedure call mode and both symmetric mode, the messages are exchanged in pairs. Okay, and these message exchanges, the way NTP works is basically there is a pair of message exchanges, and NTP relies on a sequence of these pairs of message exchanges over the past. So it looks at the history. Okay, and for every pair of message exchanges, the NTP will calculate an estimate for offset between the two clocks. So the messages are exchanged between two devices. So it basically will provide an estimate for what the offset is, okay, and also a delay, which is a transmit time for messages between the two devices. Okay, and then it also does filter dispersion, which is basically estimate error or in other words quality of results, and based on the accuracy of the server's clock and consistency of the network transit time. Okay, it does this filter dispersion. I'm not going to talk a lot about filter dispersion. This is going to be one of your reading actually, and I will put a homework question actually, how this filter dispersion works. Okay, so I'm mainly talking about how offset and delays are calculated. Okay. And basically, it uses this data to find a preferred server. Okay. So here is the pair of message exchanges. Okay, so you send a message from here from server A to server B. Okay, and then the server B replies with a message to server A back. Okay, so that's basically the pair of messages. Two messages are M and M prime. Okay, now each message here contains the local times when the previous message was sent and received. So it not only includes its own time, but it will also include. So for example, when M prime is sent, okay, it will basically include the time when M prime was sent and when the previous message M was received here. And the same thing, because this is like these pair of messages, it's like a pair that's going on one after the other, So you have basically every message that is exchanged, it contains when the last message was received and when this message was sent. Okay. And the reason why you include this, yes?
Professor, if server A and B are in different time zones, do these time or M primes have timestamps that are universally set?
So basically the time here that we are talking about is actually the time, I forget the exact date, I think it's something.
So is it epoch time?
Sorry?
Is it epoch time?
It's an epoch time, yeah.
January 1st, 70? Like that?
Probably January 1st, 70 or something, yeah. So it's basically that time since then. Okay. So it's not really referring to any time zone or anything like that. Yeah. So So the reason it needs to include this time is because, again, because you're using UDP. Okay? Remember that in UDP, messages may be lost, right? And so when the messages are sent and received, you need to basically keep track of which message is being replied to and which message was sent and those kind of things. Okay? So when this message is sent, okay, so let's start from here. So when this message is sent, one of the things M will include is the time, Ti minus 3. Okay. Now this message is received at Ti minus 2. So when M prime is sent, M prime will include actually Ti minus 3 and Ti minus 2. Okay. And the reason it needs to include that is because the server has to make sure that this reply is coming with respect to this message. Okay, because we are using UDP. So this message may have been lost. So you want to make sure which message is being replied to. Okay. So using this these pair of messages, you calculate offset and delay. Offset. Okay. So OI, which is basically the offset, OI is basically the offset that's calculated from these two pair of messages, is the estimate of the actual offset between the two clocks as computed from this pair of messages, and DI is the total transmission time for the message pair. Okay. Let's see how this is done. Okay. So if you look at the previous message exchanges, you will see that Ti minus 2, and I'll go back to that slide, Ti minus 2 is going to be Ti minus 3 plus T plus O. T is the transmission time, O is the true offset. Okay, we don't know what that is, but that's a true offset. And T, we don't know either T or O. T is the transmission time, O is the offset. So if you look at these two, Ti minus 2 and Ti minus 3, okay, so Ti minus 2 minus Ti minus, so what it is saying is, okay, that Ti minus 2, which is the time that the message is received, okay, is whatever the time then it was sent, plus the offset between the two clocks, plus the transmission time of this message. Okay, you got that? Okay. And then similarly, Ti, which is the next message, next message, okay, is the same equation. Ti is Ti minus 1 plus T prime. T prime is the message transmission time for M prime. Okay. And here the offset is because here, since we added the offset, we have to subtract the offset in the reverse direction. Okay, is this clear? These two. Okay. Now this is just algebraic manipulation. If you add these two, you will and then do a few things. You will see that T plus T prime. So if you add these two, you'll get T plus T prime is going to be equal to Ti minus 2 minus Ti minus 3 plus Ti minus. Okay. Now T plus T prime is basically the latency. T plus T prime is basically, T is the message latency for the first message, T prime is the message latency for the second message. Okay. So that's, and the other thing that you can do is instead of adding, if you subtract one from the other and do some algebraic manipulation, you will see that O, which is this quantity here, O, the true offset, will come out to be this. Okay, it's just algebraic manipulation. Okay. Now, when you look at this true offset O, what we know is these things, right? We know these 4 times. Okay. What we don't know is this, right? Okay. So basically, what you do is you estimate your offset to be this. Basically, you ignore this part, okay? And that happens to be your error bound. Okay. So if you do this way, then your error bound O turns out to be between OI, whatever the true offset will be the one that you estimated, OI, minus Di minus 2 and plus Di minus 2. Okay. That's basically the estimate, error bound. Okay. So Di is of course the measure of accuracy of the estimate of this offset. Okay. Now you'll notice what this is saying is that the T prime minus T. Now suppose your system is such that your communication is symmetric, meaning that the latency for sending the message and latency for receiving the message to M prime and M, if they are equal, then this will turn out to be 0, right? T prime minus T, because in that case T prime will be equal to T. Okay, so in that case your offset, your estimated offset will be equal to the true offset. Okay, so there is not. Okay, but in general, the message delays are not, latencies are not symmetric. Okay, so basically shorter and more symmetric the round trip time, the more accurate an estimate of the current time. So that's basically what your estimate is going to be, the offset. Okay. Any questions about this? Okay, so how does NTP work with this? What NTP does is it basically calculates this offset and OI and DI, okay, these pairs, and it retains the most recent, 8 most recent pairs. Okay, so it's basically doing this at regular intervals, okay, and then it's keeping these 8 pairs, and based on that it applies filter dispersion. This is something that, as I said, I'm not going to cover here, but we'll learn that through the through our homework. Okay? And through this, basically, it calculates the one that it finds to be the most accurate OI, and that's the one that it uses. It examines values from several servers. Okay, look for relatively unreliable values, to filter them out. Okay, and these things are pretty straightforward. Basically, based on the type of data it is receiving from various servers, it may switch from one server to another server, from one stratum to another stratum, and so on. And as we say, once it calculates the offset, it will basically modify the frequency, its own drift rate. Remember the thing that I talked about in the previous class, which is to control the frequency of the frequency at which you update your counter. So basically, you update your drift rate accordingly. Okay. Now, as I said, NTP is pretty much there in every computing device. Okay. In Windows, there is a time service called W32 time. In Unix, there is a daemon process called NTPD that runs regularly. Basically, contacts the server, gets the time, and synchronizes it. Linux also was using NTP, but more recently, I think back in 2013 or 14, they started implementing their own version of NTP, and they are calling it N-timed. Supposed to be much more efficient than NTP in the previous version. There is no official release of N-timed, although it's available over the internet and people have been using that. But so far there is no official release of N-timed. Also, this software that they're building is not portable to other operating systems. Okay. The timestamp that somebody asked this question, it's a 64-bit timestamp, 32-bit second and 32-bit fractional second, which means that there is a theoretical resolution of 2 to the power of minus 32 seconds, which is about 233 picoseconds. Okay. And yeah, the epoch that is used is January 1, 1900. Okay. And which means that it will roll over in 2036. Okay. And so the future, there are RFCs for how to address this problem. Future versions may extend this to from 64 to 128 bits. The SNTP is basically same as NTP, except that it doesn't use this filter dispersion metric. Okay. So SNTP solely relies on that message exchanges. Okay. So all it does is this, only relies on this, okay, and uses this to estimate the time. So it doesn't look at the history or statistics and those kind of things. Okay. So SNTP is a much simpler version of this protocol. Okay. So that's basically what SNTP is. Basically, the time offset is calculated as T1 minus T0 plus. This is basically the same formula that we saw for
algorithm 1.
Sorry?
Algorithm 1.
Yeah, no, not algorithm. Well, it's probably the same as that, but it's basically this thing. This. Okay.
But it doesn't use the 8 messages, just one?
It doesn't use 8 messages. So it's basically NTP uses 8 messages so that it can actually identify which data is more reliable and things like that. And in fact, based on the data that it receives, it can switch the server, saying that this server is less reliable now, and those kind of. NTP doesn't do anything like that. SNTP doesn't do anything like that. Okay. So that's SNTP. Any questions about network time protocol? As I said, this is one of the longest protocol in use for a very long time. Version 4 came out, I think, in '92 or something. So it has been in use for a very long time now. Okay. So and it has been doing its job pretty nicely. Keeping pretty much all computing, including all embedded devices, they use this. Any questions? Okay, so what I will do is so what we have talked about so far is we talked about event ordering and we talked about the true time. Okay, now when we think about building our distributed systems, okay, we don't rely on events. What we actually rely on, if you think about exchanging data and information, is what we are sending is messages, not really, Remember, when we talk about events, when a message is sent, that message actually is comprised of two events. There is a send event and then there is a receive event. Okay, and the send event and receive event, and we were basically talking about ordering and all, but it was all between the events, not necessarily between messages. Okay, and that has actually an implication. So the next thing that I will do is I'll talk about ordering. I'll extend the ordering of events to ordering of messages. So now we are going to look at message ordering. Okay? And again, it's important to understand the difference. I guess it will become clear from the first slide here. Okay? So maintaining an order in the delivery of all message exchange in the distributed system is very important. Okay? And the message, it's important to understand the difference between two events that occur on a device here whenever we are using sending messages. Okay? So when a message is received, there is an event called message receive, and then there is an event, it's an artificial event that we call message delivery event. Okay? And the order in which the messages are received, so you send a message and the message is received on a destination, right? The time at which that message is received, or if you're sending multiple messages, the order in which those messages are received, they are completely determined by your underlying protocol that you're using. So if you are using UDP or TCP or any other protocol, okay, that protocol determines the order, okay, and the message received. Okay. Now the order of delivery of message to a higher level application is determined by yet another layer that we build on top of this message exchange system. Okay. So what I'm saying here is you have our, the basic message exchange protocols like UDP or TCP or any other message exchange protocol. Okay, and you have an application running here, your distributed application. Okay, the idea is this is what is called the middleware layer. Okay, and the idea is that you basically use this middleware layer. You implement a software there. Incorporate a software there that will implement what is called an ordered message delivery layer. Okay. So in this case, this event is what is called message receive event. Okay. So this is a message receive event, okay. And then this event, okay, is what is called message delivery event. Okay. Now the idea is that when a message is received, okay, the application doesn't see that message immediately. Okay. So it's basically message received, your middleware layer will see that message. Okay. The application is going to see that message only when this event is occurs, which is what we call message delivery event. Okay. Now why do we do this? Okay. Now, actually, before I describe this middleware layer is actually a very important concept in distributed systems. Okay. And it is actually used for providing a variety of services to the application. Okay. So in this case, when I'm talking about delivery, here we are trying to control the order in which an application sees various messages. Okay. So basically, it could be, let's go back to our application that we talked about before, which was the airline reservation system, right? In that case, if we are basically building let's say we receive a message and read the message and we want to basically reserve a seat, okay? In that case, our middleware layer will ensure that the messages are received in a total order. And I'll talk about total order. It means that if you have replicated servers, every server will see those messages in the same order. Okay? That's not guaranteed by your message receive event, so it's something that you have to make sure, and that's what your message or delivery layer will do that. Okay? The middleware actually is much more than simply providing ordered message delivery. It can implement many other kind of services. So for example, fault tolerance. Okay? So you might want to have redundancy in your distributed system where you can tolerate failure of a server. Okay, and so you want to implement some service. That's basically an example of a middleware layer. Yeah.
Yeah. Generally, a message is sent from one process and received by another process, right?
Right.
So in that case, if you say a message coming out of a process to be a message delivery event and a message going into another process to be a message received event, that will make sense. But
no.
In this case, you are talking about
the message coming out of a process is message send event.
Okay.
So now we are actually talking about 3 different events. One is message send, message receive, and message delivery. Okay. Now message receive and message delivery, both of those events are occurring on the receiving process.
Okay.
Receiving machine, not receiving process. Okay.
Yeah.
Okay. So fault tolerance is an exact example of this is what you will implement at the middleware layer. Okay. But anything else, like security, admission control, load balancing, all those are basically examples of middleware layer services. Okay. So basically, your underlying system is system software is essentially your operating system, and including basic network stack, TCP/IP stack. Okay. On top of that, you basically build your middleware layer. Okay. And on top of middleware layer is where you build your applications. So why ordered message delivery? I've been hinting at that. So database updates, replicated objects. So one way by which you basically improve the availability of a server of a service is basically you replicate the service. Okay. Now when you replicate the service, one thing that happens is you want to make sure that these multiple different replicas, they are consistent with one another. So you make a change in one replica, you want to make sure that the same change is made in all replicas. Okay. And so now basically you face this problem, right? Suppose you are applying a sequence of updates on a replica. You want to make sure that these updates are applied in exactly the same order at every replica. Okay. So that these replicas are consistent with one another. Okay. The question is, how do you apply updates in the same order? Okay. So again, there you need to be able to order your messages. Okay, so that your replica update application will basically see these messages, in all machines in the same order. Okay, that's the basic idea. Okay, there are different types of message delivery ordering. Okay, FIFO is something that TCP implements. Okay, which is just if a process is sending say 2 messages, M1 followed by M2, then and another process receives both of these messages, then it will basically see M1 before M2. So that's basically what TCP is. So that's a FIFO. Okay. There is a causal order. I will talk about what causal order is. Okay. And then there is the total order. And then there is total order based on causal order. Okay. Okay. So FIFO ordering. Now, this is important to understand. I know I have been saying that there is a difference between ordering of messages and ordering of events. Okay. So what is FIFO ordering? Okay. Let's say you have messages M1 and M2, and they are sent from the same process. Okay. And the relation is that send M1 happened before send M2. Okay. So this is a happened before relation. Here we are talking about events, so we can define our happened before relation. Okay. What FIFO delivery order says is every process that delivers both M1 and M2 must deliver M1 before M2. So basically, if we think in terms of our middleware layer, what we are saying is that and just to make this thing clear, let's say we are using UDP for message exchange. Okay, because if we are using TCP, FIFO order is already guaranteed. Okay, but suppose we are using UDP. Okay, then let's say this layer here Okay, it receives a message M. Okay. The thing is that this layer may actually keep M here in a buffer, okay, until it is sure that every message that was sent before M has been seen by the application already. Okay. So it may actually delay the delivery of this message M to the application. Okay. All of you understand? So if you take this example that M1 and M2 and there is this happened before relation, right? Now suppose you are using UDPs to send this message, M1 and M2. Okay. Then it could be that M2 arrives here first, right? M2 can come first before M1. Okay. So what this layer is going to do is it's going to hold this M1 here in the buffer. It will not let the application see this M2. Okay, until it receives M1 and delivers first M1, and only after that it will give M2 to the application. Okay, so it's basically imposing this FIFO ordering on messages. Okay. So that's basically FIFO ordering. Okay. How can we implement FIFO ordering? This is very straightforward actually. TCP does that. A simple way. How can we implement FIFO ordering?
Comparing timestamps.
Comparing timestamps, that's one way of doing it, because these messages also, remember that the key thing here is they are sent from the same process. Okay? So you can compare timestamp. But the problem is this. Let's say you receive a message and it says that this message was sent at 10:55. Okay? Can you deliver that message?
Header sequences?
Sorry? Add sequences, right? Because not only you need to know when the message was sent, but you need to know if there was what messages were sent before that, right? So what you want to basically maintain is a sequencer. Okay? So each message will have a timestamp, but that timestamp will be basically a sequence number. Okay? So when I receive a message, I see at the sequence number, I see sequence number 3. Okay? I'll keep a record what was the last message I delivered to the application. Okay? If the last message I delivered, its sequence number was 2, then I know that this message can be delivered. But if I see that the previous message that I delivered was sequence number 1, then I cannot deliver this. I will hold this message here. Okay? Until I receive this message with sequence number 2, and I will deliver that first, and then I will deliver this message. Okay? So that's basically the idea. Okay? And that's basically described in the words here. But that's the general idea. You maintain a sequence number CI, initialized to 0. When you send the message, you include the timestamp, which is basically the counter value. Okay? And when you receive a message, you deliver that message based on this. So that's FIFO, very straightforward. Okay? Now, causal ordering is interesting because it kind of translates this idea of FIFO ordering to multiple processes. Okay? Because FIFO ordering, we are talking about pair of processes, it's the same sender. Now, causal ordering, to see it before I talk about all this, see in a picture is the following. And we actually see that all the time. If you use any of these chat systems, chat rooms and all that, where people are talking to one another, there are times when you might see a response to a question before you have seen the question. Right? Sometimes it happens. Like somebody poses a question, and there are, let's say, multiple clients there. Somebody poses a question, another client responds to it, and you receive the response before seeing the question, right? Okay. That's basically a violation of causal order, okay? Where you are actually seeing the response to a question before you have seen the question. Okay. So in a picture, basically you can imagine, let's say you have 3 processes, okay? And let's say you send a message. Let's talk about multicast here to make it simpler. So you send a message, M1 here, M1. So this is a multicast message, M1. Okay, this is what will happen in at least logically, that's what happens in a chat room. And after receiving M1, this process responds with message M2. Response M2. Okay. Now, let's say you are using UDP or even TCP, but let's say UDP. Okay. It can happen that this message here, the original M1, is delayed for some reason, right? Because this connection is slow, some link is slow there. Okay, so it can happen that you can see M2 before actually you have seen M1. Okay, And so in a real system, when we think about ordering and, this violation of causal order can happen all the time. Okay. Now, obviously, this is not desirable, right? And so what you want to implement is a layer, okay, that will make sure that the application sees messages that are where the order is, is respecting this causal order. Now, how do we formally define causal order? Okay. So, delivery of messages in an order in which that is consistent with the happened before relation of the corresponding send event. Okay. So, what this is saying is that if send M happened before send M2, okay, now we are talking about happened before relation. So, M1 and M2 may not have been sent from the same process now. Okay. So, for example, here M1 is sent by this process and M2 is sent by this process. Okay. But assuming that M2 was sent after M1 was received here, okay, then we can say that M1 is, happened before M2. Right? So the send M1, if send M1 happened before send M2, then every process that delivers both of these messages M1 and M2 must deliver M1 before M2. Okay? That's basically the definition of a causal order. Okay. Is this clear? Now, as we saw in this example, messages may not be received in a causal order, even if the underlying protocol delivers messages in a FIFO order. Okay, so this is an example where FIFO is respected, but still causal order may not be. Yes.
So in this case, M1 doesn't necessarily have to have anything to do with the outcome of M2, it just has the potential to have the outcome.
Right. So that's a very good observation. So basically, what we are talking about here is when we say causal order, it's really a potential causality. Okay. So, basically the idea is when I am sending a message, okay, potentially the content of this message is dependent on every message I have seen so far. Okay. But it could happen that I may have seen some messages and this message has nothing to do with it. Okay. So it's really potential causality. Okay. So how can we implement causal order? Any idea? Some basic things, what we can do to implement causal order. So this was actually a very high, there was a lot of research activity in this area, causal order, total order, in late 80s and early 90s, maybe until even mid 90s. But most of the computing systems today, distributed computing systems, they will actually, incorporate some version of causal ordering and total ordering. What we are going to talk about is a set of papers actually, a few things I'll borrow from these papers that introduce the idea of causal order between messages. Okay. This is basically a paper that came from Cornell University, and they basically implement a system, they call the system ISIS. And ISIS basically is a middleware system that provides causal order, it provides total order, and it provides fault tolerance. So it's basically a group of services together, that's set of services, and together that's called an ISIS system. Okay, and actually ISIS has been used. I don't know whether it's used now or not, but it is. I know there was a time when it was used by New York Stock Exchange and some other, pretty critical services actually. So CBcast provides a causal. So one of the protocol that ISIS provides is called a CBcast protocol, and CBcast provides a causal delivery of message multicast within a group of processes. Okay. So actually, ISIS also introduced a concept of something called a process group. Okay. And the idea behind process group is that when you are building a distributed application, okay, your distributed application is going to be basically between a set of processes. Okay. And let's call that set of processes as a group. Okay. And the idea is that to an outsider, this entire set of processes will look like a single logical entity. Okay. So that's basically called a group. Okay. So a group basically is identified by a unique group ID. So there is a group 1 and group 2, okay, kind of thing. Okay. And when you want to send a message to group, you basically say I want to send a message to this group, group ID. Okay. Or you can receive a message from a group. Okay. So instead of saying that I'm sending you the message to a particular process within this group, okay, you basically send a message to the group and you receive a message from it. So it's basically group is a single logical entity. In reality, it's comprised of many processes. Okay? The other way to think about this group is anytime you think about replication. Okay? So you replicate a server, say CNN.com. Okay? You replicate it for availability, fault tolerance, and all that reason, right? So maybe there are 5 different replicas of CNN. Okay? Now, when you want to read, you don't basically specify which replica you want to read from, right? You simply say, I want to read from CNN.com, and then, you're getting your news from one of the replica. Okay? So here, the name CNN.com is in some sense that is referring to this logical entity, single entity, which is actually comprised of multiple servers and so on. Okay? So the other thing about the group members is that the group member, or in this case, let's call them each of these replicas, okay, they communicate with one another to maintain a consistent state. Okay, and each group member can communicate with every other group member. Okay, and in fact, the way ISIS was built is that the message exchanges, all message exchanges were multicast, meaning that when a group member sends a message, it will be sent to every member in the group, okay, and every member will receive every message exchange within the group. Okay. So together, these group members will basically, form a, provide some kind of functionality. Okay. So a group actually is supported by a set of protocols. Okay. The typical 3 protocols that pretty much every group will provide is, one is called an atomic broadcast protocol, second one is called a group membership protocol, and the third one is called a member recovery protocol. Okay. So an atomic broadcast protocol is basically a protocol where a member can send a message, okay, and this message will be received by every other member of the group. Okay. The word atomic is important because remember that you're implementing this on an unreliable system, unreliable network. Maybe ISIS is implemented on top of UDP. And pretty much all group communication protocols, there are many group communication protocols. ISIS was one of the first one. Okay? But since then, several group communication protocols were built, systems were built. And, but they were pretty much all of them were built on top of UDP. Okay? And so a message that is sent by a group member is either delivered by every group member or none of the group members. Okay? And this is important, because you can imagine that these messages that are sent by these different group members, they could be, let's say, update to a database. Okay, so database is replicated, and then a group member receives a request from a client, make this change in the database. Okay, so before the group member will make that change, it will basically send this update message to all the group members. Okay, yeah.
All the processes within a process group can be spread between different systems, or are they running on just one system?
So basically, when we're talking about group member, each group member is independent of the other group member. So they are probably running on different machines, and so on. So other way to think about it, again, it helps to think about a replicated system. So if let's say you have 5 replicas, okay, so you can imagine that each of those 5 replicas are managed by a group member. So you have a group of 5 members. So when you want to apply an update, naturally the other group members are also receiving requests to update, And so what will happen is that this update will be multicast within the group. Okay? All group members will receive all these updates, okay? And then they will apply a particular protocol, ordering protocol, either causal order protocol or total order protocol, and then the message is delivered. When the message is delivered, it is at that time the update is actually applied to the database, to the replica. So the atomic broadcast protocol basically says that a message is delivered either by all group members or by none. Okay? Or in other words, what it is saying is that you either apply an update to every replica or you don't apply that update to anyone. Okay? That's basically maintaining consistency. Okay? So this basically is atomicity. Okay? And the delivery order delivery order depends on what kind of application you are trying to build. Okay, so for some applications you may require a strictly total order, means that you want to make sure that all these updates are applied strictly in the same order. maybe there is another application where it is okay to apply these updates as long as you are respecting the causal order. Okay, so that's basically an application semantic that determines what order. So ISIS provides different types of ordering. It will provide a FIFO ordering, it will provide a causal ordering, it will provide a total ordering. As an application, you choose which ordering you want depending on your semantics, the application semantics. The group membership protocol actually ensures that there is a consistent view of what this group membership is, right? Because over time these members will fail, right? I mean that's because these group communication protocols are supposed to be fault tolerant. Okay, so some members may fail. Okay, so let's say we have 5 members, 1 member fails. Naturally, once a member fails, you can never satisfy atomicity because this member will never receive this message, right? So you can never apply any updates. Okay, so at that time, what happens is that the group membership protocol steps in and it redefines the group. Okay, it basically throws out this failed group member from the group. Okay, now group membership protocols are very complicated. The question is how do you first determine whether a group member has failed? Okay. And then you have to basically build what is called a consensus among all the other group members that we all agree that this member has failed. Okay? And that those protocols can be very complicated actually. So we'll look at one protocol, group membership protocol, as an example. Okay? So this is basically group member, and then you have a member recovery protocol where a member which had failed wants to rejoin the group. Okay? Then it has to basically we have to recover the state of that group member. So there's a recovery. So those are the 3 key protocols for a group system. Okay, so ISIS is basically an example of a group system, and I'm going to talk about just one protocol from that, which is the CBcast protocol, okay, which basically implements the causal delivery. The algorithm that you will see is very similar to the algorithm that we looked at when we were talking about building the vector clocks. Okay? But the difference is the vector clocks were applied to the events. Here, CBcast, we are applying to the messages. Okay. So each group member I will maintain a vector time, which is called VTI. It's basically identical to what we did in the vector clocks. So it's basically a counter, a vector of counters. Okay. All entries in this are initialized to -1 in the beginning. Okay. Now, before multicasting a message M, a member I increments this and attaches the timestamp to M. So that's basically again same what we were doing in the case of vector clocks. Okay, so whenever you want to send a message, okay, you increment your counter, the VT, the ith counter of your vector time, and increment that, and then you attach the entire timestamp. So you are attaching the entire vector, okay, to this message. That becomes a timestamp of the message. Okay, that timestamp. Okay. Now, when a message is received, okay, this member J is going to delay the delivery of M until these 2 conditions are satisfied. Okay, so this is basically we're talking about this middleware layer. Okay, so you receive this message. This message contains a timestamp with it. Okay, now you will keep this message in a buffer until these 2 conditions are satisfied. The first condition is basically, so we are looking at member J now. Okay, so this, when I say VT of J, what we are meaning is that it's the vector that's maintained by J. Okay, and the TM we are talking about is basically the vector that came as a timestamp of the message. Okay, so we are looking at 2 vectors now. Okay, the vector of the message of the process that's received this message, and the vector that was associated with the messages of the timestamp. Okay, so the first condition that has to be satisfied is the ith entry. Remember, I is the member that sent the message. Okay, so the ith entry of my vector, I am the receiver. Ith entry of my vector should be exactly equal to the ith entry in the timestamp minus 1. Okay, and think about what's going on here. Okay, it's essentially implementing FIFO. This first condition. Okay, so the idea is that every time I send a message, okay, I increment my own counter, right? So if I am I will, every time I send a message, I will increment VT of I. Okay, so basically when I receive a message, clearly this is the first time I'm seeing this message. Okay, So what I want to make sure is that I have seen every message that I sent before this message was sent. Okay. So let's say you send a message to me. Okay. I receive this message. Okay. Now before I can deliver this message, I want to make sure that I have seen every message that you have sent before this message. Okay. That's basically what this first condition is doing. Okay. Now the second condition is a little bit more involved, because now this is talking about what happens when the message was sent from this I, received at another process K, and then K sent a message, and I have seen this message already. So it's basically kind of looking at a bigger loop now. Okay? So it's looking at every other entry of this vector, okay, other than the I, the sender who sent the message, every other entry. And I want to make sure that my entry, every other entry, is actually larger than or equal to the corresponding entry that is there in the message timestamp. Okay. This is a little bit involved, I agree, but basically what's going on here is that let me try to explain this through a picture. Suppose here is process I, okay, and it has its vector time Vt of I. Okay, so Vt of I has all these entries, right? I mean basically the n entries here. Okay, and J receives this message, right? Now it's important to understand what do these values mean. Okay, in some sense the message that I'm sending, okay, this is the message I'm sending when, let's say this particular value is say 5, the first entry. Okay, what that means is that I have actually seen 5 messages from member 0. Okay, and after that I'm sending this message M. Okay, so when J receives this message, what J wants to make sure is that J also has received the first 5, at least the first 5 messages from 0 before it can deliver this message M. Do you follow that? Okay. The idea is that when I send a message, there is I have some state, right? And potentially the new message I have sent, it depends on the entire current state, which is basically every message I have received from every other process, every other member. Okay. That's what basically is determined by this each value in this vector. Okay. So when I send this message, I have current state. When the message is received, okay, I want to, before I can deliver this message, I want to make sure that every message that was seen by I, okay, I have also seen those messages before I can deliver that message to my application. Okay, that's basically what this is doing. Okay, so the example of the chat room that I was talking about. Okay, what will happen is that let's say I sent sent a question. Okay, posted a question on the chat room. It was sent to me and it was sent to you too. Okay, you got that message, and then you send a response. Okay, now when I receive this response, the question that arises me is, how do I make sure that I can deliver this response so far or no? The way I will determine is that when you send that response, okay, you will include that timestamp. In that timestamp, you will record that you have seen this question, basically using that, the I sent that message. So the ith entry in that vector will say that this message was sent. I will look at my vector. If the ith entry is actually less than the ith entry in the timestamp, that means I have not seen the question yet, so I cannot deliver the response yet. That's the basic idea. Okay, I would like you to think this more carefully. It will make sense maybe to take some examples and see that this actually, once you follow this, it actually will deliver the message. It will implement the causal delivery of messages. And then when you deliver the message, you will update your timestamp, your timestamp with using the vector. This is actually similar to the vector clock that we talked about. You update the way you update your vector. Okay. So this is basically the algorithm, the basic algorithm that CBcast uses for implementing causal order. Okay. There is actually another implementation which I want to talk about for causal order. Okay, and that is it's basically a protocol. It's called psync. Okay, psync stands for pseudo synchronization. Okay, And psync is actually again psync actually provides just a causal ordering of messages. Okay? And then a group communication system is built on top of psync, okay? Which provides all these services that ISIS provides, like the causal order, total order, and membership, group membership protocol, and all that. Okay? So the psync provides basically causal delivery of messages multicast within a group of processes. Okay? Each group member will maintain a context graph with nodes representing messages, edges representing causal ordering between messages. Okay? I'll go through this with a picture to explain what's going on. Okay? But all messages have unique IDs. That's the important thing here. That is, every message that is exchanged in this group of processes, they have a unique ID. How do you construct a unique ID? Well, you include it's basically a pair of IDs. So you include the sender ID and a sequence number. Okay. So with that pair, basically you build a unique ID. So every message has a unique ID now. Okay. Because each process is maintaining a sequencer. So every message sends and increments the sequence number. Okay. And of course, in that case, two processes may have the same sequence number, but then their sender ID is going to be different. Okay. So that basically makes sure that you have different message IDs, unique IDs for every message. How does this work? Okay. Let me actually give an example to. Okay. Let's go over this and then I'll build a context graph. Okay. So basically, before you multicast a message M, okay, a group member will append to M message IDs of all leaves in the context graph. Okay. This is actually let me. So let's say we have three processes. Okay. Say process P0, so with three group members, P1 and P2. We have three processes. Okay. Now each process is maintaining what is called a context graph. Okay. So context graph. So initially there is a root, of course. Okay. Root of the graph. So that's initial part. Okay. Now when you send a message. Basically, in the beginning, let's say, I'll just write down here. So suppose it so happens that the sequence is that P0 sends a message, okay. Sends a message, okay. And let's call this message as M00, okay. The first message that P0 is sending, okay. So in the beginning, basically you will put an arrow in your context graph, okay. And this is basically what will be M00, the message M00. Just for to understand what's going on, let's put another process here, P1. Let's say at the same time it sends a message, and let's call that as M10. So first message. Okay. So what P1 is going to do is in its context graph, it's going to put a message M10. Okay. Now suppose at this point, P2 receives say M00. Now, here's the key here. That is, when M0 is sent, it basically, along with the message, what you attach is basically the message IDs of all the leaves in your context graph. So basically, when M0 was sent, of course, all you had was a root. So there is no context here. It's the very first message. Okay. Now, when P2 receives this message, P2 can deliver this message if the leaves, the message IDs that are attached to M00, if all those message IDs are already present in P2's context graph. Okay. So in this case, of course, there are no message IDs attached with M0. So it can go ahead and deliver M00. So in its context graph, it will see M00 like that. Okay. At this point, let's say P2 receives M10. Now, when P2 receives M10, it looks at what is attached to M10. It will say there is nothing attached because only the root. Okay. So P2 can deliver this message. It will basically attach this like that here, M10. All of you understand this? What's going on? Okay. Similar thing will happen basically when, let's say, when P0 receives M10, it will say that, M10, there is no context to it, nothing is attached to it. So P0 is going to attach like that, P10, and similarly when P1 receives it, it receives M00 like that. Okay. Now at this point, suppose P1 sends M11. So P1 sends M11. Okay. Now, when you send a message, you include the message IDs of all your leaves in the context graph. Okay. So in your leaf right now, you have for P1, it's M10 and M00. Okay. So when M11 is sent, it will include the message IDs which are M10 and M00. Okay. So it's basically, in some sense, M11 will include message IDs which are basically M10 and M00. Okay. Now, when this message is received by, say, P2, okay, what P2 has to do is it has to look into this message ID that I attached and make sure that these messages are actually there in this context graph. Okay. In this case, the answer is yes. Okay. So in which case, basically, it can go ahead and deliver M11, and it will put it in its context graph with this arrow. Now P11 when it sends M11, it would have done this. Okay. Now let's say P0 hasn't seen this message M11 yet. Okay. But at this point, say P2 sends a message, and let's call that as M20. Okay. So P2 sends a message. Okay. Now for P2, there is one leaf only. So that will be included in M20. So M20, when it is sent, okay, it will include M11 as its context. Okay. So basically the picture will look something like this here, M20. Okay. Now let's say P0 receives M20 now. Okay. Now when M20 is received, P0 is going to look into its context and see that, well, there is M11 here. It doesn't see M11 in its context graph. Okay. So this is where P0 is going to delay the delivery of M20. Okay. Because at this point P0 knows that M20 potentially depends on another message which is M11, but I have not delivered M11 yet. So I'm not going to deliver M20 because I'm just going to keep it. I'm going to deliver M20 only after I have received M11. Is that clear? So even though P0 has received M20, it's going to keep in a buffer separately, but it's not going to deliver it. Okay. Suppose at this point P0 wants to send a message, and so let's say it's going to send M01. Okay. So in its context graph, it has two leaves right now. So M01 will be attached like that. Okay. And your M01 will have a context. The context will be M00 and M10. Are of you with me here? Right? What's going on? Okay. So this will be the context, M00. And when this message is received, let's say by P2. Okay. So P2 receives this message M01. Okay. It sees that the context is M00 and M10. Well, it sees that yes, it has M00 and it has M10. Okay. So it's basically, it knows that it can deliver this message, M01. Okay. So it will deliver M01. Okay, and it's going to basically follow the as far as the arrows are concerned, it's going to follow the same the dependency. So basically, it will basically put arrows like that. Yes.
So as this grows and grows and grows, at what point do all the processes decide everybody's seen M00 and I can disregard that? Because otherwise it's going to...
It can keep growing, yeah. Okay. So that's a good point. Basically, the thing is, obviously, the graph can keep growing. At some point, you want to prune the graph. And basically, you need to basically figure out, somehow that a message has been received by every process, right? And we'll look at that. Okay. There is a way to figure that one out. Okay. Any other question?
Where is this ordering taking place again?
This is that middleware.
This is the middleware.
That's the middleware. So P-Sync that we are talking about is middleware. So underlying protocol is UDP when you're sending messages, receiving. That's UDP. Okay. It's the P-Sync which is implemented on top of UDP is what it is doing. It's maintaining its own buffer. It's maintaining its own graph. Okay, and then whenever it is able to attach a message to its graph, that's when it delivers that message to the application.
Okay.
Any other question? Yeah.
Can these processes ask for retransmission?
Right. Yeah. So we'll talk about that. You know. Now, so at this point, the P0 of course knows that it cannot deliver M20. Okay, but it actually knows much more than that. Okay, because when it receives M20 and M20 was here. Okay, not only knows that that it cannot deliver, but it also knows that it hasn't received this message M11. Okay, so possibly M11 was lost. Okay. Okay. And this is basically for the mechanism that is used to recover lost messages. Okay. That is, in this case, the way psync is implemented is when P0 sees this message, it sees that M11 is missing. Okay. Using the messages IDs are constructed so that it knows the sender of this message, right? Because the sender ID and sequence number. So then it basically sends a unicast message to P1, and it will ask it to retransmit this message to it.
Yeah.
Okay. So that's basically a mechanism for recovery from message losses. Okay. Now, in the same vein, I would like to describe that's basically recovery from message losses. This is basically implementing fault tolerance. There are actually two ways by which a typical message loss or reliable message delivery is implemented. Okay. One is what we just described, and this is sometimes called negative acknowledgement technique. Okay. Negative acknowledgement technique. Okay. What negative acknowledgement technique basically means is that based on the system that you are building, somehow you learn that you have missed a message. Okay. So for example, in this case, you learned because message IDs were included in the message. Okay. And when you learn that you have missed a message, you explicitly asked for that message from the sender using a retransmission or something. So that's basically a negative acknowledgement technique. Okay. The other technique is, as you can imagine, the other one is what is called positive acknowledgement technique. And that's the technique that is used in something like TCP, right? So in TCP, or if you remember in network systems, your sliding window protocols, they use basically a positive acknowledgement technique where you send a message, and as a sender, when you send the message, you expect an acknowledgement for the message that you sent. Okay? If you don't see the acknowledgement within a particular time interval, you resend the message. Okay? That's basically a positive acknowledgement technique. Okay? This is a negative acknowledgement technique. Okay? Now, typically at the middleware layer, most of the protocols, fault-tolerant protocols that you will see, they will adopt negative acknowledgement technique. Can anyone guess why they use negative acknowledgement?
It's less work.
It's less work.
Because it uses UDP. There is no acknowledgement in UDP.
Right. Well, but the thing is, you can imagine that you can imagine implementing something similar to sliding window at the middleware also, right? You send a message, and you expect an acknowledgement. You don't, then you resend the message. So you can implement that algorithm at the middleware layer also.
But this reduces the traffic.
Reduces traffic. That's the key thing here. Okay? That when we say that UDP is unreliable, it is true that it's unreliable. Messages may be lost, but there is a basic assumption that most of the time it will end up delivering the message correctly. Okay? So most of the time the messages will be delivered. Think about email. Like once in a while, email do get lost. But almost always, like the emails are delivered, right? So that's the idea, that the failures are possible, okay, but most likely they will be rare. Okay, so you want to basically implement a system where your overhead to recover from failures the overhead is going to be small. In a positive acknowledgement, you will be sending an acknowledgement for every message sent. Okay, so the overhead is basically 100% for every message. In a negative acknowledgement, your overhead is much lower because you send a request and transmission only when a message is lost. Okay? And hopefully the messages are not lost frequently. So your overhead is going to be much smaller. Okay, so I will stop at this point. We will continue discussing psync a little bit more. Okay? And then we'll talk about total order and a little bit about membership protocols.